Students, next we are going to see force between two parallel current carrying conductors. So, a current carrying conductor produces magnetic field in the region around it. So, here we are going to consider parallel conductors. So, A and B are two parallel conductors separated by a distance r. Let I1 be the current flowing in A and I2 be the current flowing through B. So, due to the flow of current I1 in a magnetic field is produced around this conductor. So, the magnetic field at this point B1. So, when we apply corkscrew rule, the direction of the magnetic field is perpendicular to the plane of the blackboard acting inwards. So, I am representing it by into mark. So, this is the magnetic field. The amount of magnetic field is given by B1 is equal to mu naught into I1 by 2 pi r. So, in vector form we can write B1. So, the unit vector in this direction is obtained by, let us consider this as x-axis, y-axis and z-axis. I cap, j cap and k cap are the unit vectors. So, we are having three axes, x, y, z. So, the unit vector along this x-axis is I cap. So, here the magnetic field is opposite, inverse. So, minus I. So, minus I cap. In this magnetic field, this conductor B is located. Let us now consider a small element of length dl. So, this dl element will experience a force. The force experienced by this conductor is given by F is equal to, or dF is equal to I2 into dl cross B1. So, substituting the values, we will have dF is equal to I2 into dl mu naught I1 by 2 pi r into k cross I cap with the negative sign. So, this will give df vector is equal to mu naught I1 I2 by 2 pi r into dl into j cap. So, this tells, so the direction of the force is obtained by using Fleming's left hand rule. So, when we apply Fleming's left hand rule, the middle finger represents the direction of the flow of current. So, this is the direction of the flow of current, this is the direction of the magnetic field and this is the direction of the force. So, force is acting in this direction. So, this tells that this elementary small element of the conductor B is attracted by the conductor A by a force F. So, force per unit length is given by F by L is equal to minus mu naught I1 I2 by 2 pi r into j cap. So this is the force on the conductor B due to the current carrying conductor A. In a similar way, when we consider this conductor B will also produce magnetic field. So the magnetic field produced by this conductor B on the conductor A is given by B2. B2 is, the direction of B2 is perpendicular to the plane of the blackboard acting outwards. So the magnetic field acting outwards is represented by a dot. In this magnetic field, this conductor A is located. So similarly, if you consider a small element, the force on this element of length dl due to the current carrying conductor is given by dF is equal to I1 into dl cross B2, where B2 is given by B2 is equal to mu naught into I2 by 2 pi r into I cap. So when it is substituted here, we will have dF is equal to mu naught I1 I2 by 2 pi r into dl k cross I. So that will give dF is equal to mu naught I1 I2 by 2 pi r into dl into j cap. So this is the force on that element. Force per unit length. Force per unit length is given by F by L is equal to mu naught I1 I2 by 2 pi r into j cap. So when we find the direction of the force, again when we apply Fleming's left hand rule, this is the direction of the flow of current, magnetic field, this is the direction of the force. So force is acting in this direction, that is, this conductor B attracts a small element towards it. So this tells that when current flows in the same direction, the force between the two conductors is attracted. So if you consider two conductors, so in these two conductors, I1 and I2 are flowing in the same direction. So when we consider two conductors, and if the current through the conductors are in the same direction, so I1 and I2 are the currents, they are in the same direction. If it is so the case, the force between the two conductors is attractive force. On the other hand, if you consider two conductors, they are separated by the same distance, and when you see the flow of current flows in opposite direction. Here current I1 is flowing in one direction and I2 is flowing in the opposite direction. If it is so the case, the force between the two conductors is the repulsive force. So from the force between two conductors, we can obtain definition for ampere. So force between two conductors is given by F is equal to mu naught into I1 I2 by 2 pi r. So this is the force per unit length of the conductor. Now in this expression, if I1 is equal to I2 is equal to 1 ampere, 1, and the distance is equal to r is equal to 1, when it is substituted, expression for force per unit length is equal to, you will have mu naught by 2 pi, that is 4 pi into 10 power minus 7 by 2 pi. So pi answer. So force per unit length is equal to 2 into 10 power minus 7. So ampere, this expression help us to define ampere. So define definition for ampere. Ampere is the constant current that flows through two identical conductors separated by a distance of 1 meter produces a force of 2 into 10 power minus 7 Newton. So if we have two conductors, if the two conductors are separated by a distance of 1 meter, and if we allow constant current to flow through them, if they produce a force of 2 into 10 power minus 7 Newton per meter in that conductor, then the current that flows through the conductors are 1 meter, 1 ampere. So once again I will tell the definition. Ampere is defined as the constant current that flows through two identical conductors separated by a distance of 1 meter produces an attractive force of 2 into 10 power minus 7 Newton per unit length of the conductor. So students, in this part we are going to see what is the torque acting on a rectangular current carrying coil kept in the magnetic field. So first of all we have seen when an electric charge moves a magnetic field, it will experience a force. Secondly, we have seen when a current carrying conductor is kept in the magnetic field, it will experience a force. Then we have seen force between two parallel current carrying conductors. Now we are going to see what is the torque experienced by a rectangular coil kept in the magnetic field. So we are going to consider a rectangular coil. That rectangular coil is kept between the pole pieces of a magnet. So we are having pole pieces of a magnet which will produce uniform magnetic field. So magnetic field lines will flow from north pole to south pole. So they produce uniform magnetic field. In this magnetic field, we are having a rectangular coil. So we are having a rectangular coil. So L is the length. Let this coil be represented by PQ or S. L is the length and B is the breadth of the loop. So this is also breadth. So we are drawing a normal. This normal makes an angle theta with the magnetic field. So this is the direction of the magnetic field. Angle between the normal and the magnetic field is theta. So current I ampere flows through the coil. So for simplicity, we are considering single turn. So this coil, the single turn of the coil is made up of 4 conductors. PQ, one conductor, QR is another conductor, RS is another conductor, and SP is another conductor. So we are going to find out what is the force on each conductor. So first of all you consider PQ. In PQ, this is the direction of the flow of current and this is the direction of the magnetic field. So magnetic field and the flow of current are perpendicular to each other. So force on PQ. So force on PQ is given by IL cross B, that is I PQ cross B, that is I PQ is IL cross B. The magnitude of the force is given by F is equal to B I L sin 90. So sin 90 is 1. Therefore, force on PQ is given by force on PQ is equal to BIL. So this is the force on PQ. Let it be the first equation. What about the direction of the force? So direction of the force is obtained by using Fleming's left hand rule. Flow of current, magnetic field. So when you apply this is the, so it will act in this direction. This is the direction of FPQ. Just the direction of the force. Now you consider QR. Next we are going to find out what is the force on QR. So QR is equal to I into QR cross B. This QR is nothing but breadth. So I into B cross B. That is B IB sin. So when you consider the magnetic field is acting. So direction of the magnetic field and the direction of the current is this angle. This angle is equal to 90 minus theta. So you will have 90 minus theta. 90 minus theta is cos theta. So you will have force on QR is equal to BIB cos theta. So when you find the direction of the force, so direction of the force is given by Fleming's left hand rule. So this is the direction of the flow of current, magnetic field. So the force will act along this direction, F into QR. Then consider this RS. So force on RS. Force on RS is given by I into RS cross B. This RS is nothing but the length. So IL cross B. That is magnitude of the force is given by F into RS is equal to BIL sin 90. Because when you consider the direction of flow of current and magnetic field, they are perpendicular to each other. So force on RS is equal to BIL. So when you consider the direction of the force by applying Fleming's left hand rule, this is the direction of the flow of current. Direction of the flow of current. This is the direction of the magnetic field. So it acts in the downward direction. So F into RS. Now you consider this SP. Force on SP is given by force on SP is equal to I into SP cross B. That is I into B cross B. So the magnitude of the force is given by BIB sine 90 plus theta. So this is direction of flow of current. This is the magnetic field. So when you consider this is the normal, so this angle you have to 90 plus theta, that is equal to BIB cos theta. This is the force on SP. So when you find the direction of force, this force will be along this direction. So F into SP. So these are the four forces on this rectangular loop. So among these four forces, when you consider this FQR and FSP, they are equal in magnitude, opposite in direction. They are acting along the same line. They are collinear. Since they are collinear force, equal, opposite and collinear, they cancel each other. But when you consider the force FPQ and FRS, so when you consider the forces FPQ and FRS, they are equal in magnitude. So FPQ is equal to BIL and FRS is also equal to BIL. They are equal in magnitude, opposite in direction. They do not lie along the same line. So two equal and opposite force separated by a distance will constitute a couple. So they will form a couple of force. The net effect of the couple is to rotate the body. So it will tend to rotate the loop. So the rotating effect of couple is obtained by finding moment of couple. Moment of couple is called torque. So torque about this AB is given by tau is equal to B into FPQ. That is equal to B by 2, one of the force into perpendicular distance. That is, torque is obtained by finding moment of couple. Moment of couple is equal to force into perpendicular distance. So force is FPQ. Perpendicular distance is this distance. This distance is B by 2 sin theta. So that is equal to B by 2 sin theta into BIL. Similarly, the force due to torque of the force FRS is equal to FRS into B by 2 sin theta. That is equal to B by 2 sin theta into BIL. Therefore, total torque is equal to B by 2 sin theta plus B by 2 sin theta into BIL is equal to B by 2 sin theta, B by 2 sin theta, B sin theta into BIL. So we will have BI LB sin theta. What is this LB sin theta? LB, L in length into breadth is area. So BIA sin theta. So this is the torque on single loop. If you consider the coil is made up of N turns, then torque on the coil is given by NBIA sin theta. So this is the torque experienced by a rectangular coil when it is kept in the magnetic field. So torque experienced by the coil is equal to NBIA sin theta. whenever the plane of the coil is parallel. So we have seen this coil is inclined to the magnetic field at an angle theta. So theta is nothing but angle between the magnetic field and the normal. When the plane of the coil is parallel to the magnetic field, then the value of theta is 90 degree. At that time, the torque experienced by the coil is NBIA. So NBIA is the torque experienced by a coil when it is kept in the magnetic field. So thus we see that when a current carrying coil is kept in the magnetic field, it will experience a torque. Torque is given by NBIA sin theta. If theta is equal to 90 degree, then the torque experienced by the coil is NBIA. NBIA.